Greeting everyone, my name is Khalid Mohammad Al-Fuwail. I am an undergraduate student who is studying a bachelor degree in Control and Instrumentation Systems Engineering from King Fahd University of Petroleum and Minerals in Saudi Arabia. And now I'm presenting to you one of my recent projects that is about utilizing a sliding motion control, which is one of the best controllers in dealing with the nonlinear systems, and I enhanced this controller by RNN, which is one of the AI algorithms. All of that is to maximize and enhance the power production from the wind turbines in the farms and etc. So I will show you the code and the simulating that I did in MATLAB. So yeah, have a nice watching. Here, ladies and gentlemen, here we have the MATLAB. As you can see here, we have the wind speed. Okay, it is the variable wind speed, and here we have the wind turbine, and the wind turbine gives its torque and the power extraction to the PMSG, the permanent synchronous generator, magnetic synchronous generator, and it gives it to machine side converter, which is the rectifier. And we have here the control approach, our approach here to enhance the power extraction for the system. So as you can see here, we have here the wind speed. It is whether it is a variable or constant wind speed, and we have here the wind turbine. Here we have the rotor, the turbine rotor, and the pitch angle controller, and etc. And we have here the PMSG with the setting variables, okay? And here we have the machine side converter, as I mentioned before, and the controller, the most important thing in this whole simulation. Here we have the MSC, which stands for the sliding motion control, as you can see here. And here we have the approach, the integral sliding motion control, and here we put the code, as we mentioned in our research paper, and this is the equation for the approach. And here we have the updating subsystems and the parameters, of course. And here we have the RNN for the uncertainty estimation prediction. Here we have the weight updates. We keep updating the parameters, as you can see here. And we have here the code for the RNN. We have the function d hat, etc., and we have the function and the exponential, and etc. And it gives at the end the d hat with some summation error. And here we have the PI control, which is the proportional integration controller. And yeah, the other rest systems. And here we have the measurements and calculation and conversion from ABC to DQ conversion, and etc. And so let us together run this whole simulation and see the result. Okay. Okay. As you can see here, it is running. So let us wait for the let us make it do the compilation, and we will Okay, now we have finished the compiling, and now let us go and see the result. Okay, so the results shall show here, as you can see, but let us run it together. So we collect the simulation data. Okay, we collected them, and let us see together the plots. We have many plots. We have the motor speed plot, and we have the d-axis current and q-axis current as well, and for the voltage, of course. And we have the power. We made the power capture coefficient for the plot from the figure, and the electromagnetic torque as well. The turbine power, the wind speed, and the tip speed ratio. The turbine speed and the rotor speed, they are similar, of course. The blade pitch angle, and the lumped uncertainty for the estimation. And we combine many of them in one plot. So let us do a running for them. Okay, and now we can see all together the plots. Okay, let us wait for them to do the. Okay, as you can see here. Okay. Okay, as you can see here. Okay, here we have the d-axis voltage and q-axis voltage. As you can see here, it is involved in the time for seconds for 40 seconds. And here we have the power capture coefficient with the blade pitch angle and the tip speed ratio. Their values here, because regarding the power coefficient is small, between 0 and 1. And we have the turbine speed and the motor speed. They are similar because they are similar. When the turbine is moving in rad per second, the rotor speed are similar. There is some delay due to the mechanism and etc. And this is the lumped uncertainty. As we can see here, at the beginning there is a diverge. But as the time passes until 40 seconds, between 15 to 40, it becomes converge each other, which proves a high prediction for the uncertainties. These uncertainties could be some errors in the mechanism or in capturing the power and etc. So this system or the RNN will predict all these uncertainties and give it as a feedback to the controller, which is the sliding mode control. And we have here the as we can demonstrate it there, and here the lambda, the wind speed from 0 to 40. And here we have the power. As we can see here, we have maximized the power by 400,000 megawatt or 400 kilowatt for around here it is 5. Let us say here it is maybe 9 until 40. So around 31 seconds we have keep an optimal power generation for the power. And we have here the torque, the cumulative conductivity torque, and etc. And here you have the current difference and the actual, as you can see here, for the d-axis and the q-axis. And that's all. Thank you so much.